Whitney. I'm a developer advocate. I'm here with Duffie Cooley.
I'm Duffie Cooley. I'm the field CTO at Isovalent. I'm also a member of the CNCF's TOC committee, Technical Oversight Committee, and I'm super excited to be here talking to you about Cilium.
I'm so excited too. So Duffie and I just spent the last 2.5 hours together on an enlightening stream. Duffie just taught me and our live audience at the time what Cilium is. Everything we've learned is before us right now. So we're making a short video recap for you, those of you who don't have time to watch the full length conversation that we had.
I would start with if you're going to understand Cilium or you are going to make use of Cilium, then one of the first things that you want to do is understand what eBPF is. eBPF is to the Linux kernel as JavaScript is to your browser, because it allows you to basically inject new functionality or manipulate existing functionality in the Linux kernel, leveraging programs that you built that are specifically built to do that in the Linux kernel.
So during their stream earlier, Duffie was like, okay, it's a kernel technology enables us to inspect and manipulate any call to the Linux kernel. And so I was just taking it in, my jaw kind of dropped, and Duffie's like, I can see what you're thinking.
How is this safe?
Yeah, that's exactly what I was thinking.
Because I was thinking it too. The very first time I ever heard that phrase, I was like, but why?
It can't be safe. How is that okay? The reason that it's safe is because there's an eBPF verifier. So before you're able to inject code into the Linux kernel, this eBPF verifier is verifying your code's not an endless loop. It has various mechanisms to say this code is safe. It's going to verify your code doesn't crash, and then your code can go into the kernel via eBPF.
And it's true for every eBPF program. There are no eBPF programs that are pre-compiled. They actually have to be built every time you want to inject something in the Linux kernel. And then the next thing we talked about was...
What is Cilium? Yeah.
And we talked about Cilium being basically a networking product. Its goals are to solve networking observability and security in cloud and legacy environments, and not just for Kubernetes environments, but for those legacy environments and how your Kubernetes environments interacts with all of those things. We're trying to solve all of those things, and we're doing it at native kernel speed.
At native kernel speed, so fast. I often have heard of Cilium every time I've encountered it out in the wild in the context of service mesh. But your definition of Cilium is broader than service mesh. It's like a whole networking technology. What distinguishes Cilium from a service mesh?
I find it super interesting that you have only heard of it in context of a service mesh, because most people have interacted with it most primarily as a CNI or a container networking interface.
Ah, okay.
And that's what distinguishes it, is that we do a lot more than service mesh. We actually are able to satisfy all of the requirements of container networking. We're able to improve the observability of things because we're able to gather so much more context at the kernel about what's happening, who did what connected to what, whether we allowed that or not, implement things like network policy. We're able to do just a ton more.
So let's dig into that a little bit in terms of, we talked about it in a bit of a linear way, how does even the process of using Cilium kick off? So first, in Kubernetes, your kubelet is creating a pod. The kubelet reaches out to the CNI, to the container networking interface, and it's like, hey, give me a networking stack for the pod. In this case, Cilium is the CNI implementation. So Cilium does that, but it also generates an identity for that pod, and not the IP address, because the IP address is going to change. And then it also attaches an eBPF program to the pod network namespace. This I didn't understand because I'm a noob, but the pod has a network namespace. The whole host machine has a network namespace. The containers each have a network namespace. So the level we're working at here is the pod network namespace. And now Cilium attaches an eBPF program to that pod network namespace. That opens up the world to a lot of different cool things that you can do. So first and foremost, what is that program that's attached to the pod network namespace? What's it do?
So the first thing it does is it actually starts to generate events whenever it sees any sort of network event. Anytime an application tries to talk to another application, anytime an application tries to talk to it outside the world, to the internet, and it starts generating events whenever those things happen. And those events give you unprecedented visibility into what's actually happening at the network layer across the set.
You said something during the stream. You said,
we have effectively solved the observability problem.
Observability is solved. Such a huge statement. We did it. It's done.
Yeah, check.
Exactly.
We're able to do that because we are now gathering, like even before we do any enforcement, before we do anything else, we're already gathering more context about what's actually happening in this networking layer and presenting that context to you in useful ways through a UI, through a CLI, than you would ever have had without it.
So that's the observability piece. And then we went into how it adds security. So Cilium can implement network policy with eBPF. One of the rules of Kubernetes networking is that every pod should be able to talk to every other pod of the cluster on any node. But you don't really want every pod to be able to talk to every pod. So you put network policies in place to restrict which pods can talk to each other. And so Cilium implements network policy with eBPF. It is using this stream of events that we talked about that's helpful for observability. And for every event that's generated, Cilium is weighing that event against network policy and saying yes or no. So this means that the network policy is happening at a packet level. With Cilium, previously it happened at a session level. How is that beneficial?
First, I'll clarify a little bit. In that eBPF program, we're not just like watching for events that have happened. We're instrumenting the kernel such that when an event happens in the Linux kernel, the following things happen, right? One thing that happens is we gather context and we push that context down to user space so we can make use of it and understand what we're observing. And the second thing that happens is we implement things like network policy. So when that event happens, we look at that event, we look at the context we've gathered, we determine from that, should we allow this traffic or disallow this traffic, right? We make that network policy decision based on the context that we're gathering at the kernel. We're not watching our own events. We're watching what's happening at the kernel. And what that allows us to do is respond to traffic or make those policy decisions as close to the source as can possibly be, which is way more efficient than a lot of the other solutions that are out there that have to wait for that traffic to move down into IP tables, to have to wait for that traffic to be trying to leave the cluster, to have to wait for all of those things before they actually make their decision. We can make that decision basically right at the application layer. The other difference here is that because we're making that decision on a per packet basis, when you make a change to policy, that change is immediately effective. There's this construct in firewalls that's called allow established, which is the idea that any established connection should not be interrupted by the firewall. It should only be new connections that are measured or determined whether they should be allowed or not, or denied. In our case, we actually look at every individual packet as a thing that should be evaluated, not every session, which means that when you make a change, it's immediately effective.
So then we talked a little bit about networking. So that's the security piece. And then we jumped into networking. So Cilium has lower latency. But what happened before without the socket layer load balancing, if a pod wants to talk to another pod and both pods are running on the same machine, what happens is the pod talks to the host talks to the IP table, the IP table talks to the host, and then the host talks to the pod. And that's how that information would get from one pod to another pod. But with Cilium, a network socket is opened and a pod can talk directly to another pod instead of having to go through IP tables because that trust is established at the kernel level.
And we've determined at the kernel layer that this is basically just two sockets on the same host. We allow the TCP session to become established, and then we just touch the two connections together so that they can actually communicate with each other directly, cutting out a lot of CPU time and all of the other work that is necessary to be able to allow for the passage back and forth between these things, because we know that these two entities are allowed by network policy to communicate, and we could just allow them to communicate directly.
And then Cilium can also act as a Kube-Proxy replacement. So Kube-Proxy ships as part of Kubernetes binary. So it's a component that implements services from traffic coming into a node. So it usually uses IP tables or IPVS. But Cilium can replace this.
And it's not just traffic coming into the node. It's also traffic actually moving between pods and services like node port or services like cluster IP. So typically what happens is this is all, like you said, implemented in IP tables or IPVS. But in our case, we've implemented all of that in eBPF, which means that we make that routing decision, we record the routing decision and maintain that decision through the life of the session. We do all of that in eBPF.
All the rules were all together in one unit, and the whole IP table would need to get reloaded if any rule changed. But now these networking rules are atomic. They're happening independently of one another, and lower CPU has a lot of benefits. And then finally, we talked about Cilium can also handle load balancing, BGP, which stands for Border Gateway Protocol, IPv6 addresses, egress gateways, and overall, it just improves connectivity, not only within the Kubernetes cluster, but the world. Improves connectivity.
Exactly.
So other infrastructure too, that's not necessarily Kubernetes specific. It improves connectivity there.
And then we got into Cilium as a service mesh, and we talked about like the different use cases. Like, what are people adopting a service mesh to accomplish, right? And some of the things that they're trying to accomplish are things like encryption or advanced load balancing or improved observability or layer 7 network policy or being able to do things like route traffic to a new deployment, but only a percentage of that traffic, like percentage-based routing, and being able to do things like service discovery. And then we got into basically how Cilium goes after each of these individual use cases. On the encryption side, Cilium can do this in a couple of different ways. It can just opportunistically encrypt all traffic leveraging IPsec or WireGuard, but it could also leverage a newer mechanism that's called mutual authentication, where we decouple authentication from encryption. We're able to transparently to the application allow for authentication to happen between two different pods. And once that authentication is established, we ensure that traffic is encrypted between those pods, but we leverage IPsec or WireGuard to encrypt that traffic rather than leveraging TLS to encrypt this thing.
The cool thing about that is MTLS is specific to HTTPS. And now you can do this security with other protocols, like gRPC would be a very popular one.
Or Kafka or anything of any of those,
Kafka.
which is pretty neat. And the next use case we had was like advanced load balancing. To solve some of these problems, we've implemented things like Gateway API, which allow us to do things like percentage-based routing, or really kind of represent sort of like the V2 or V3 of ingress. When we think about like all of the complex things that people really want from ingress, that Gateway API really allows us to service a lot of those things. And we implement all of that with Cilium and Envoy in the back.
So percentage-based routing based on traffic headers, or if it's coming from a certain place, all of the above. So then we talked about L7 network policy, L7 being the application layer. So we have our example of L7 traffic. It might be HTTP traffic. Maybe the policy is that it's allowed between X clients and X web service, but only on certain paths and only for gets and not for deletes. And Cilium could absolutely handle those kinds of advanced network policy rules. And for many protocols too.
And has been for quite a long time. Like even before Cilium decided to kind of come into the service mesh space, like we've been handling things like layer 7 network policy and things like improved observability for the entire time. It's always been like a first class thing for us. Even the idea that identity, which is another component of like MTLS, is something that we've actually implemented since the beginning, 7 years ago.
That's old in Kubernetes land.
Yeah.
And then our final thing is back to observability, which is something we really want to drill home because Cilium shines here. So other service meshes do a deep packet inspection. And so the inspection points are happening if it's a sidecar service mesh, like next to the running container. But the Cilium, that observation point is happening at the kernel level. You talked about context. This provides more context. Will you say more about that?
What we're able to do with Cilium, because we're actually kind of operating in the Linux kernel, we can not only capture what's happening at the networking layer, but also capture what's happening at that application layer. And that means that we have a ton more rich context about what's actually happening at that piece. In a lot of the deep packet inspection models, you can do things like understand that this traffic came from this pod and it went to these destinations, but you're not able to understand like which individual process made this connection. In the case where somebody gets a reverse shell on an application that you have running in your stack, you wouldn't be able to see that had happened because you wouldn't know which process is generating this traffic. You just see the traffic going by. In our case, we can show you that. We can say this was a batch process. It started an SFTP to push data out. It connected to this external host. This is how many bytes went by when it did it. This is the policy that allowed for that traffic to actually happen. So there's a lot more context, a lot more visibility into what you're able to do.
It's mind-blowing. It's so cool. What would you like to say, like some final words about Cilium to wrap up? And maybe like if someone's curious, where do they go next to learn more about Cilium or perhaps play with it?
So if you go to isovalent.com/labs, you can find labs that cover all of these individual pieces and parts and give you a hands-on way to learn about all of this capability. And if you go to cilium.io, you can learn a ton more about the open source project that is now a graduated CNI within the CNCF. And if you go to eBPF.io, you can learn a ton more about eBPF, not just what we do with it, but what others are doing with it in the space.
Do you want to say anything else about Cilium before we say goodbye?
I think I will say it's the best. And if you have questions about it, and if there's something I can do to help, just let me know. I'm Maui Lion everywhere.
Thank you so much for watching our enlightening recap. Have a wonderful, wonderful day. And thank you for sharing your time with us.